If you place a single positive charge in an empty space, the electric potential radiating out from it follows strict, predictable rules. The strength of the field depends entirely on your distance from that center point, creating perfect, expanding spheres of influence. But space gets far more complicated when we introduce an electric dipole. A dipole consists of two equal but opposite charges, one positive, one negative, separated by a small distance. Even though the combined total charge of this pair is exactly zero, they don't simply cancel each other out. Instead, they warp the surrounding space into a complex asymmetrical field. This creates a mathematical headache. For a single charge, calculating the potential at any location is easy. You just measure the distance to the center. But with a dipole, you have two distinct centers pulling the math in opposite directions. To map the energy around a dipole, we have to stop measuring absolute distance from a single point and start navigating a two-dimensional map of spatial geometry. Let's drop a random observation point into the empty space surrounding our dipole and see what exactly is happening to it. We'll call this point P. First, we measure the straight line distance from the positive charge to our observation point, giving us our first mathematical variable. Then, we measure the distance from the negative charge to that exact same point, creating our second competing variable. To find the total energy at point P, we apply the superposition principle. This rule states that the total response at a given point is the algebraic sum of the individual influences acting on it. We just add the positive and negative potentials together. The relative distances dictate the winner. If we move point P closer to the positive charge, the positive potential becomes mathematically stronger and dominates the location. Conversely, if we sweep point P toward the negative charge, the negative potential takes over. Every coordinate around the dipole is locked in a continuous tug-of-war. The exact distance ratio strictly determines the net energy at any location. Tracking two shifting distances is cumbersome. Physicists simplify this by drawing a single central vector from the exact center of the dipole to point P and measuring the angle, called theta, between that vector and the main axis. This setup introduces the dipole moment. The dipole moment is a single vector pointing from the negative charge to the positive charge that quantifies the system's overall polarity and strength. To make the math elegant, we use the far field approximation. This is a mathematical assumption where we calculate the potential from a location so distant that the size of the dipole itself becomes negligible. At this massive scale, the competing distances cleanly condense into a single formula, known as equation 2.15. Notice that the angle theta takes center stage. The cosine of theta acts as a strict directional multiplier. Your exact angle relative to the dipole moment completely controls how much potential you experience. By zooming out, we stop treating the dipole as two competing charges. Instead, we treat it as a single, highly directional projector of electrical energy. We can test this equation by looking at the geometric extremes. If we place our observation point directly on the main axis, dead ahead of the positive charge, the angle theta is 0 degrees. Since the cosine of 0 is precisely 1, the multiplier is at its peak. This specific alignment yields equation 2.16. This location experiences the strongest positive electric potential the dipole can possibly generate. Now we sweep the observation point exactly 90 degrees along the arc, until it sits perfectly perpendicular to the dipole, right on its equatorial plane. Here, the cosine of 90 degrees is 0. Because that multiplier drops to 0, the electric potential along this entire dividing plane completely vanishes. There is 0 net potential energy here. The dipole possesses a built-in mathematical blind spot. Its own internal symmetry perfectly neutralizes its electrical influence on anything occupying that perpendicular slice of space. While the angle of observation dictates where the potential exists, the distance determines how quickly it disappears. This chart compares the energy decay of our two systems over distance. A single point charge loses potential gradually, following a shallow 1/r curve, but the dipole's potential decays much more aggressively, following a steep 1/r² curve. From a distance, the positive and negative charges appear to sit in the exact same spot. Because they are so close together, their respective fields aggressively cancel each other out as you move away. A single point charge projects its influence deep into space. A dipole, however, is a highly localized phenomenon, a fierce, direction-dependent